Greetings, Jim here, AG6IF. This is part 4 of our series of working through Gordo West Technician Ham Radio Class Manual, Booklet, Study Guide. My name is Jim. I'm in Southern California. My ham radio call sign is AG6IF, Alpha Golf 6 India Foxtrot. Thanks for watching. Hopefully we can work through the general class manual and maybe even get done on this session if my voice holds up. And so anyway, we're on page 15 of this manual, and we're working through the questions in a verbal fashion. We're going to get into electronics, a little bit of the electronic stuff that's involved with the ham radio license, and I'm going to show you how to solve the questions, all of them, using some solvers right here. We've talked previously about 300 flying monkeys, frequency to wavelength conversions, and how to solve them. Now we're going to talk about EIR and PIE, pi. Everybody likes pi. Electricity is renewable. Now when you go to take your ham radio exam, I'm hoping what you'll do is get a piece of scratch paper from your examiner and sit down at your spot and write these solvers right on your notes, on your scratch paper. You will use them for answering the questions on the exam, and I'll show you how to work this. Okay? We're also going to talk about how to calculate antenna lengths and so forth, half wave, quarter wave, and full wave antennas, the equations for those, 4, 6, 8. Who do we appreciate? That divided by the frequency is the length in feet of a half-wave antenna. Okay, so there we go. Okay, we're on 145. We're working through the questions. Let's switch over to my Gordo West PowerPoint presentation here. We're on question T5, Alpha 05. What is the electrical term for electromotive force, EMF? Electromotive force that causes electrons to flow in a circuit. Well, that's called voltage. And I don't know why, but it's represented with an E. Electromotive force, voltage. So try to connect those two together. Voltage is E, okay? What is the basic unit of electromotive force? Basic unit is the volt. And that's where we get the voltmeter and so on. That is the volt. It is a unit of measure for electromotive force, otherwise known as voltage. T7D01, which instrument would you use to measure electric potential or electromotive force? Well, a voltmeter is what you use. Come in all kinds of shapes and sizes. Here is a voltmeter that also does some other things. It does other readings as well. But you set it on voltage, and you have to select AC or DC in this case, and there you are. Voltage is measured in parallel with the circuit. So, and we'll talk about that a little bit more. Okay, voltmeter. Next question, what is the correct way to connect a voltmeter to a circuit? You connect it in parallel. One side, one lead to one side, the other lead to the other side. So all kinds of voltage power distribution. Here's a power pole. It's got the plus and the minus, red and black. You would connect your voltmeter, one lead to the side and one lead to the side to measure the voltage in the circuit. And that's called parallel. Which of the following battery types is rechargeable? Rechargeable batteries, nickel metal hydride and so on. NiCads are rechargeable. A lead acid gel cell is rechargeable. Lithium ion is rechargeable. The answer to the question is all of the above. There's a type of battery that's not rechargeable. We'll get to that. Okay, but all of those are rechargeable. All right, we are on A11. We're on page 146. A11, which of the following battery type is not rechargeable? If you're old enough to remember the carbon zinc batteries, they're still around, but not as popular. Carbon zinc is not rechargeable. If you try to recharge them, they will make a mess inside of your device. They can leak, so on. Not rechargeable, carbon zinc. Okay, keep that in mind. A06, how much voltage does a mobile transceiver usually require? A mobile transceiver requires 12 volts. That's generally what your car uses for its accessories and its starter. And its other accessories, a cigarette lighter plug is 12 volts. A mobile radio requires 12 volts. And it's DC, it's direct current, versus AC, like what you'd have in your house, alternating current. Direct current is what you have in your mobile or in your ham shack, go bag, or so forth. DC, okay? A11, bottom of 146. Question is, where should the negative return connection of a mobile transceiver power cable be connected? Okay, so we want to connect our mobile radio directly to the battery. Directly to the battery or the engine block ground strap. So directly to the battery or the engine block ground strap. Okay, no other place. You don't want to connect it anywhere else. A03 on 147, what is the name for the flow of electrons in an electrical circuit? The answer is current. Current is the name for the electrical flow. It's measured in amps, and you measure it with an ammeter. Similar to a voltmeter, an ammeter measures the current flow in a circuit. And how is an ammeter usually connected to a circuit? D03. D03, it's connected in series. The ammeter has to become part of the circuit. Instead of measuring the edges of the circuit in a parallel fashion, it becomes part of the circuit and measures it in a series fashion. So the current flows through the circuit and through the ammeter, and that's where you get your reading from. Okay? Just remember series for an ammeter. There's a graphic on bottom 147 explaining how you measure the current in a light bulb, in a flashlight, and how the connections would happen. So bottom, if you're following along, it's right here. Okay, A01, we're on top of page 148. Electrical current is measured in which of the following units? I think we just talked about that. It's measured in amps, amperes, amps or amperes. Okay. 07, which of the following is a good electrical conductor? Good electrical conductors, for example, is copper. That is the answer to the question, copper. All right. What is the name for a current that reverses direction on a regular basis? Like this, it goes back and forth in the wire. That's alternating current, AC. You find that usually in your home, and it runs back and forth about 60 times per second. Its frequency is 60 hertz, in other words. That's in the US. Other parts of the world have different frequencies, like 50 hertz is common, but in the US it's 60 hertz. Okay. D01, which of the following devices or circuits change an alternating current into a varying direct current? Okay, so what does that is a rectifier. There's a rectifier built into a wall wart charger for USB, for example, a little black plug-in transformer that you plug your cell phone into or some other rechargeable device. It changes AC current to DC current using a rectifier that's built in. And then it lowers the voltage down also, usually to 5 or 12 volts maybe. In the case of a laptop, maybe it's 18 volts. What is the name for a current that flows only in one direction? You might guess that to be direct current, DC. Batteries provide direct current. If you put them in backwards, the device will not work. The batteries must go in the right direction, the plus on the right side, the minus on the correct side. Okay, batteries. All right, we are 149, B02, Bravo 02. What electronic component allows current to flow only in one direction? It's a diode. A diode allows current to flow only in one direction. There are two electrodes to a diode, and the question is, what are the names of the two electrodes of a diode? And the answer is an anode and a cathode. I think of it as the anode is the aft end of it, and the cathode is the front end of it. Okay, and current flows only one direction through the diode. It's like a one-way switch, one-way valve. All right, B06. Basically, there's not much room on a diode. I'm looking around to see if I have one here. They're very, very small, and so they put a stripe on the diode on the side of the cathode. It actually matches the diagram, the way they draw this device. It's got a little stripe on it. So the question is, how is the cathode lead of a semiconductor diode usually identified? And of course, the answer is with a stripe. There's a diode right here, actually right here. And you can see how the stripe corresponds to the stripe on the device. We're on 149. There are some pictures of the diode. Nice pictures here. Okay. Stripe is the cathode. 01, what electrical component is used to oppose the flow of current in a DC circuit? And that is a resistor. It is labeled as R with our solver. That's the R. It stands for resistor, resistance, and that is going to be used as part of the circuit we're going to use to calculate. Okay, resistor, R. What instrument is used to measure resistance? Well, a ohm meter is used to measure resistance. The unit of measure of resistance is the ohm. This device here has a ohm setting. It's right there. It's omega. Okay. This device will also measure resistance. Ohm meter. All right. Find my place again here. Okay, let's see here. A02. The question is, what type of component is often used as an adjustable volume control? Let's see, adjustable volume control. Well, I've got the knob for one, but it is called a potentiometer. It is a variable resistor. Here's a knob that you could put on a variable resistor, and it will change the resistance from low to high. They're typically used as volume controls. Okay, it's called a potentiometer. What electrical parameters is controlled by a potentiometer? Well, the resistance is controlled by a potentiometer, from low resistance to high resistance. Okay, we're on 08. Which of the following is a good electrical insulator? Insulator, glass is a good electrical insulator, and that's the answer to this question. An insulator blocks the flow of electrons. The old telephone poles used to have glass insulators on top that the wires were hooked to. And a lot of people collect those today. What type of electrical component stores energy in a magnetic field? Magnetic field, the component is called an inductor. It is a coil of wire. It's basically a coil of wire, and it stores energy in a magnetic field. If you take a piece of wire, wrap it around a nail, and hook the wire to a 9-volt battery, you will create a little electromagnet. When it's on the battery, the nail, the tip of the nail will pick up magnetic objects that are ferrous metal. Okay, it stores energy in a magnetic field. There's an electrical component that's composed of a coil of wire. It is called an inductor. An inductor is a coil of wire. It stores energy in a magnetic field. We've been talking about the inductor. There's a great photograph on the bottom of page 150. Okay, 150. You'll see that on a circuit board as an inductor. All right, what is the ability to store energy in a magnetic field called? Well, we know it's an inductor. It stores it in, it's called inductance. Inductance. That's the ability to store energy in a magnetic field. Okay, CO4. What is the basic unit of inductance? The basic unit of inductance is Henry. It was invented by a fellow by the name of Henry. I'm sure of that. That is the inductance. Millihenries, microhenries, and so forth, depending on the size. TF5C12. What is meant by the term impedance? Okay, so impedance is very important to answering a lot of these questions. Impedance is the measure of the opposition to AC current flow in a circuit. Impedance is similar to resistance, but impedance is AC, usually used in AC. In DC, they use the term resistance. So impedance is the opposition to AC flow. Okay? C13, the unit of impedance is also the ohm. Unit of impedance is the ohm, just like the unit of resistance is the ohm. 01, what is the ability to store energy in an electrical field called? Okay, that's a different device. It's called capacitance. Capacitance is the ability to store energy in an electrical field. It is a capacitor. The device is called a capacitor. The basic unit of capacitance is the farad, F-A-R-A-D, usually microfarad or picofarad, very, very small picofarad. Okay, that's a capacitor. Let's see, CO2, CO4. The capacitor stores energy in an electrical field. Electrical field is different than a magnetic field. The electrical field is how a capacitor stores energy. Capacitor is two plates separated by an insulator, might be air or some other material, and it stores electricity between those two plates. On top of page 152, there's a capacitor before it's been rolled up. There's also some photographs of capacitors in the book elsewhere too. Okay. 05, what type of electrical component consists of two or more conductive surfaces separated by an insulator? We just talked about it. Capacitor, that is the name. Capacitor, they can be very large, very small. There's different types of them, but they all work in the same exact way. All right, let's see here. 08, what electrical component is used to connect or disconnect electrical circuits? What do you think? A switch? The switch is the right answer. Electrical circuit like your overhead lights or anything that an outlet in your home, or the switch that turns the turn signal on in your vehicle, in your mobile vehicle, in your car. Switch, okay? You're all going to get those right. Guarantee it. Okay, A09 on top of 153. What electrical component is used to protect other circuit components from overloads? How about a fuse? Okay, we've all seen the little glass fuses. We've seen the other kind in the car. Got one here. Maybe I can come up with one real quick. Here's a fuse. This one happens to be a 5 amp fuse. Okay. It protects other components or the cabling from overload. That 5 amp fuse would be used in some small wires, pretty small wires. Which of these components can be used as electronic switch or amplifier is a BO3 question. The answer is a transistor. A transistor can act as a switch on or off, okay? Or if it's used in between on and off, it can be used as an amplifier. That's how an audio amplifier works. It's how an RF amplifier works. Okay, uses a transistor or a series of them to either increase the signal, in the case of an amplifier, takes a small input signal and makes it bigger, or it can be used as a switch, turn all the way on or all the way off. BO1, what class of electronic components is capable of using a voltage or current signal to control current flow? And that once again is a transistor. You can put a current in the third terminal to force the device to either pass current or not pass current, as the case may be. It's kind of an electronic switch. All right. BO5, we're at the bottom of 153. Which of the following electronic components can amplify a signal? You probably guessed it, transistor. If it's operated in that proper fashion, it can become an amplifier and amplify the signals. Transistor is going to have a schematic diagram. We're going to see it here. Here's one right here. And notice the arrow is pointing away from the body. This is a transistor. It's an NPN transistor. NPN. And I remember this one not pointing north. The arrow is not pointing north when it's in that orientation. It's facing away from the body. There's another transistor that has a different makeup. It's called a PNP, and the arrow is pointing towards the body. So what's that one? Pointing north. Pointing north, probably. How's that? PNP. That's with the arrow pointing towards the body. And don't be fooled if they roll it upside down. Sometimes they roll them in different orientations. But that's typically the standard orientation right there. All right, makes sense? Transistor, a very, very important device. Okay. Moving on to page 155, what is the term that describes a transistor's ability to amplify signal? Okay, the term is called gain. Gain. It has so many dB of gain. It takes a small signal, makes a bigger one. That's called gain. B10. What are the 3 electrodes of a PNP or an NPN transistor? Okay, there's 3 electrodes. Let's see here. I don't have a photograph. That's they're shown in the book on page 155, 154, and 153. Okay, the emitter, the base, and the collector. Those 3 in a PNP or NPN transistor: emitter, base, or collector. For those of you that aren't electrical engineers, which is a lot of you, that's just something you're going to have to try to remember. EBC, emitter, base, and collector. All right. BO4, which of the following components can be made of 3 layers of semiconductor material? 3 layers. NPN stands for negative, positive, negative. The answer is transistor. It's a 3-terminal device. It's either an NPN or a PNP, and the silicon is built in such a way that it's either positive, has a positive lean or a negative lean, and that's what makes the device. That's where the device gets its name from. NPN or PNP. Okay. Let's see. There is a second type of transistor called a field effect transistor. A FET. Much more used nowadays. Very high efficiency. The FET, the field effects transistor, is the abbreviation for FET, F-E-T. Talk a little bit more about the FET. in a bit here. What are the three electrodes of a FET? Okay, they can't be the same. That would be too easy. The three electrodes are source, gate, and drain. Source, gate, and drain. It's one of those things. You're probably just going to have to try to memorize that. All right, source, gate, and drain. I don't have any easy ways to remember that. Transistors replaced vacuum tubes. Vacuum tubes, like this guy here, that's the functionality of the vacuum tube was replaced when the transistor was invented in the 1950s or thereabouts. Everything started getting smaller then. All right, that's our section. Let's see how we do on the next one. Working through the Gordon West Technician Manual. Okay, and we're going to get involved a little bit with Ohm's Law now. Ohm's Law is very useful, and I've got some solvers. We'll go through how to do these questions. We're not going to do all of them. Hopefully we'll do a few, and you're going to know how to do all of them. Because once you know how to do them, you know how to do all of them. Okay, so we're on page 158, and there's a picture of the solvers and an explanation of how to use them. I'm going to try to explain it also. All right. T5A10 on 159, which term describes the rate at which electrical energy is used? Okay, that's power. You pay for power. Your electric bill has power rated in kilowatts or watts for hours. Watts per hours. Kilowatts per hours is 1,000 watts for an hour. So they measure all the watts flowing through your meter, and every month they send you a bill. Maybe they don't send you a bill if you have solar panels. Okay, speaking of solar panels, electricity is renewable, EIR. That's one of the solvers. The other one is pi. Everyone likes pi, right? Okay. You pay for power. Power is energy, and power is measured in watts. Kilowatts for thousands of watts, maybe megawatts for millions of watts. Depends if you use a lot of power. Okay, but AO2, electrical power, is measured in which of the following units? It's measured in watts. All right, here's how this works. CO8. Power is in watts is equal to volts times current. Okay, we're going to start here with pi. When you solve for one of these three items, you cover it with your finger. Or if you're solving for watts, if they're asking how many watts, you cover the P for power. Watts, power, interchangeable. And you're left with I times E. Okay? If you're solving for power, cover the P, I times E. It's that simple. They're going to give you a series of questions. They're going to give you two of the three items. And the one you're missing, you're going to cover. And then this is going to be P divided by I. Okay, you can use a calculator. If they're asking for current, amperes, you cover the I. It's going to be P divided by E. Okay, that's how the solver works. Whatever you're solving for, the unknown, you cover that with your finger, and you're left with a multiplication. In the case of here. Or you're left with a division problem. Never a plus or minus. It's always multiplication or division. All right? So let's look at some of the questions. Okay. CO9. This gets fun. And once you get this, you're going to be a lot happier. You'll be able to solve a lot of issues. How long does a battery last? Why does my cigarette lighter plug blow out in my car when I plug my CD player in, or whatever? Okay, how much power is being used in a circuit when the applied voltage, okay, we're in this one. They're asking for power, so I'm just going to cover the P. All right? How much power is being used in a circuit when the applied voltage is 13.8, okay, and the current is 10 amperes. So I is 10, and E is 13.8. So what do? We multiply 13.8 times 10. Simple, right? And the answer is 138 watts. I'm on question T5C09. So 13.8 and 10. They gave you the two values. You multiply them together, and there's your answer. Okay? All of these questions work the same exact way as this. Once you understand this, you'll be able to solve all of the Ohm's Law questions for the technician, the general, and the extra. All of them. Okay, the next question. How much power is being used in a circuit? Stopping right there, covering the P, when the applied voltage is 12 volts and the current is 2.5 amperes. Okay, they gave us 12. 12 is the E, and 2.5 is the I. So what do we get? 12 times 2.5, we get 30 watts. 30 watts. Okay, simple, right? 30 watts. That was question T5C10, bottom of 159. Okay, now we're at the top of 160. Oh, they're changing on us. How many amperes are flowing in the circuit? Okay, hold on. Voltage, so they're giving us watts and voltage, and they're asking for amperes. So they're asking for amperes. What do? That is the I, right? Amperes is I. I know it doesn't make any sense, but it's the intensity of the current. It's amperes. Cover the I. So what did they give us? They gave us how many amps flow in the circuit when the applied voltage is 12. So over here we have 12, and the load is 120 watts. So they gave us 12, and they gave us 120 for the P. 12 divided into 120, right, is 10. And it's 10 amperes because we're solving for amperes. Okay, that question, you can go back and look at these again, back up the video a little bit and double check if you're not sure. But this is exactly how all of the Ohm's Law questions work. All of them. Okay, the next one, T5DO2. What formula is used to calculate voltage in a circuit? Now we're going to move over to this one because we have our voltage here. This is how we calculate voltage in the circuit. Well, I suppose you could calculate voltage here too, but we're moving over here. And the answer is going to be voltage E equals current multiplied by resistance. E equals current multiplied by resistance, I times R. Okay, that's one of the answers in the DO2, or I'm sorry, the CO9. I'm getting behind myself here. Let me make sure I get scoot it forward a little bit. T5DO2. We want T5DO2. Right. Voltage E equals current multiplied by resistance. Just read the question carefully and you'll find the best answer. All right. T5D10, what is the voltage across the 2 ohm resistor? Okay, now we're still using the solver, EIR. Electricity is renewable. What is the voltage across the 2 ohm resistor if the current is 0.5 amperes flowing through it? So they're asking for voltage. Cover the E. We're left with I times R. For I, they gave us 0.5. And R, they were nice enough to give us 2 ohms. So 0.5 times 2 equals 1. You may use a calculator for the test if you feel more comfortable. But 0.5 times 2 is 1, and that's the answer to T5D10. All right, D11. What is the voltage across the 10 ohm resistor? What is the voltage across the 10 ohm resistor if the current is 1 amp? Okay, so they gave us a 10 ohm resistor for R, and they gave us 1 for the amps. 1 times 10 I don't think anyone needs to reach for their calculator. 1 times 10 is 10. Okay? And it's in volts because they asked for the voltage. Be careful to select the right 10. There may be another 10 in there that might be some other suffix. Just make sure you get the right 10. Okay? Bottom of 160. What is the voltage? Okay? Cover an E across a 10 ohm resistor if a current of 2 amps flows through it. So they gave us 10 for the R, and they gave us 2 for the I. 2 times 10 is 20. 20 volts. The answer is D, 20 volts. Getting it? Getting it? See how easy that is? Electricity is renewable, PIE, and of course our 300 flying monkeys. These 3 solvers, you can solve all of these Ohm's law questions and all of the frequency and megahertz and wavelength questions as well. All right? I don't think we need to go through all of these. They all work the same way. Cover what you're solving for. Okay, and then make sure you just read the question carefully and take your time to make sure that you get the right suffix. I'm going to skip forward a little bit. T5D08 on page 161. All right. Okay, we're back to we're on our solver. What is the current flowing through? So they're asking for current. Cover the I. There we go. Cover the I. Current flowing through a 100 ohm resistor connected across 200 volts. Okay, they gave us 100 for the R and 200 for the E. If we divide that, 100 into 200 should get 2 amperes, and we're solving for I with amperes. Okay, that's T5D08. All right. Okay. T5, let me find T5D03. They're asking you what the equation is. So here's the question. What formula is used to calculate resistance in a circuit? So we know it's right here. The formula to calculate resistance is E divided by I, or I into E, but E divided by I. So if we look at the answers here, resistance equals voltage E divided by current I. Okay, so you look at your solver and you can tell exactly which equation you're going to use and then find the one that matches. All right, they're never plus and minus, they're always divided by and multiplication. Okay, there's a couple plus and minus answers in the wrong answers. They're distractors. Okay, they're never ever plus and minus. So with that, you got your solver in front of you, and you've got a way to figure that out, and you understand this, you're going to get every one of those questions right. People come into the class and they're afraid of electricity and Ohm's law, and they don't understand. And when they leave the class, they're very excited that they understand. So I've seen that over and over and over again. So that's great stuff. All right, let's see where we're at here. T5D04. Let's just try a couple more. What is the resistance of a circuit? R, we're going to cover the R. What's the resistance of a circuit in which a current of 3 amperes flows through a resistor connected to 90 volts? So they gave us 3 and they gave us 90. 90 divided by 3 equals 30, right? So 30. Ohms, we're solving for ohms, and the answer is 30 ohms. B, 30 ohms, and this is the top of 162. All right. Okay, let me see here. There's a number of questions. They're all very similar. Match up the numbers they're giving you and cover up what you're solving for, and you'll get the right answer. I guarantee that you'll get the right answer. Okay, let's see how we're doing here. Gordo's rule. On most technician class questions, you divide the larger number by the smaller number. And presto, you end up with the correct answer. Okay, so keep that in mind. And the other one, Jim's advice, never plus and minus, always division or multiplication. All right, let's see where we're at here. That is it. Ohm's law. Resistance, current, power, voltage. That section, voltage, obviously, is the volt. It's E for electromotive force. You do have to get the right values in the right places. Resistance is clear. It's an R. Current is not so clear. It's the intensity of the current. It's amperes, and its symbol is I. Okay, just remember, amperes is I. Power, of course, is P. That's easy enough. And electromotive force is voltage. So just match those up, and you use these solvers, and you will actually find yourself getting a perfect score on the Ohm's law questions. Very exciting, in my opinion. All right, let's see where we're at here. We are going to talk about some electrical components. We're on page 163. 163. And what we're going to do here is look at the electrical components and what they're called and what they look like. A lot of this material, it's helpful to follow a line book. Okay, I'll try to show you a few of these. Very first question, what is the name for a standardized representation of components in an electrical wiring diagram? And the answer to that question is, hidden under my sticky note, it is a schematic symbol. Schematic symbols. Schematics are electrical diagrams that show the components. Okay, the next question here, T6, C12, what do the symbols on an electrical circuit schematic diagram represent? Of course, they represent the electrical components. 13, C13, which of the following is accurately represented in electrical circuit schematic diagrams? What's accurately represented? Okay, what's accurately represented is how the components are interconnected. Every lead is shown on the schematic and where it connects to. Okay, the way components are interconnected is the correct answer. There's a picture on the next question. If you don't have the book, I'm going to try to hold this up. What is component 3 in figure T3? And I'm going to show you what figure T3 is. What is component 3? All right, well, here we go. This is the schematic they're referring to. 3 is over here. You notice that 3 has, it looks like a coil of wire, and it's got an arrow pointing to it. All right, so a coil of wire, you know, is an inductor, correct? A coil of wire is an inductor. And anytime you see an arrow pointing towards the component, that is, use the word variable. Okay, that's variable. It can move around. When you turn the knob, the pointer can move around in the device. It's supposed to depict adjustability. So a coil of wire is an inductor. The arrow pointing in is variable. Therefore, it's a variable inductor. Okay, variable resistors exist. Variable capacitors exist. They all have that arrow. Okay, that's the variable component of that device. Okay, so a variable inductor, coil of wire with an arrow. What is component 4 in figure T3? And I'll show you what that is in a second here. Component 4. Component 4 is it's actually an antenna. Let's see if I've got, okay, is right here. I know it might be hard to see, but it's a kind of a triangle shape. That represents an antenna. Okay, DO8, let's see here. C10, DO8, let me find DO8. I'm getting a little bit lost here. Sorry about that. C10, C11, okay, DO8. Which of the following is used together with an inductor to make a tuned circuit? All right, kind of memorization. A tuned circuit needs a capacitor and an inductor. A capacitor and an inductor make a tuned circuit. Okay, so that is the answer, capacitor. Tuned circuit. There are a number of components that are listed in the book right here. If you're following along, feel free to study those. You don't need to know all of them, but there's a few of them that are on the exam, like a switch, for example, and some of the other ones. What is a simple resonant or tuned circuit? This is D11 on 165. A simple resonant or tuned circuit. Answer is an inductor and a capacitor connected in series or parallel to form a filter. So that's a resonant circuit. Okay. CO2, what is a component? What is component 1 in figure T1? Okay. Now, I'm going to show you that above my finger here. Component 1 is a resistor. Component 1 is a resistor. It's a squiggly line, and that is what a resistor looks like on a schematic. Component 2 in CO3 in figure T1, that we've talked about already, right here. What do you think that is? That is a transistor. Okay, and I believe that its arrow is not pointing north, so it's an NPN transistor, but you don't need to know about that, but that's an example of an NPN transistor right there. All right, let's see where we're at. D10, what is the function of component 2 in figure T1? That's the transistor we just talked about. What is the function of? The function is to control the flow of current. Okay, controls the flow of current. CO4, component 3 looks like, what is component 3 in figure T1? Component 3 is a lamp. Okay, a lamp is going to be, it's hard to show you this, but here's a lamp. That's what it looks like. Okay. And CO5, bottom of 165, what is component 4 in figure T1? Component 4 depicts a battery. There's a battery or power source right there. Battery. It's got long and short lines interleaved. All right. So what do you think that circuit does? The switch, the transistor conducts, and current flows through the lamp and turns on the light. That's what it does. So when a signal comes in from the front of the circuit over here, the transistor turns on and the current flows through the battery and through the lamp. You don't need to know that, but that's what's going on in this circuit. All right. DO3, let's see where we're at here. DO3, top of page 166. What type of switch is represented by component 3 in figure T2? Component 3. Okay, so we're back to components. Component 3, that is the picture. That's how a switch is depicted. That's a switch. Okay. And that happens to be a single throw, single pole. So it's a switch that has a lever that is closed or open. Single pole, single throw. Goes one way, it's either on or off. Okay. CO9, what is component 4 in figure T2? 4, transformer. That's what they look like. 2 coils of wire close together, and with a iron, those 2 lines represent an iron core. 2 coils of wire make up a transformer. Okay, there's a picture of a transformer right here. Transformer does what? It transforms voltage from one level to another. For example, it may do some other things as well. Okay, let's see. CO6, The component 6 in figure T2, 6 is how we depict a capacitor. Two lines, and usually they're parallel, but they can be, one can be shaped like a C, like a Charlie. Okay, depending on how you turn it. That is a capacitor. And if you recall, it stores its energy in an electrostatic field, electrical field. CO7, the component CO7, T2, is a T2 component 8 is actually a, find it, it is a diode, but it has two arrows emitting from it. That makes it a light emitting diode, an LED. That's what an LED looks like. It's a diode, but it has two lines sticking out from it. Squiggly lines right there. It means it's a light emitting diode. They're everywhere. Lights are LEDs now and so on. CO8, very common, very common. Component 9 in our figure here is, okay, right here. Component 9, first of all, it's got the squiggly lines like a resistor. Therefore, it is a resistor. And what did I say about the arrow? The arrow pointing back into it. That means it's a variable resistor. Variable resistor right there. Okay. Working our way through here, we are DO4 on top of 167. Which of the following can be used to display signal strength on a numeric scale? Signal strength on a numeric scale is a meter. Do I have a meter close by? I don't have a meter close by, but there's a picture of a meter right there. And it shows display signal strength, for example, on a numeric scale. Which best describes a relay? A relay. Answer A, a switch controlled by an electromagnet. So it's a switch, like we talked about, but it has an electromagnet that can pull it down or push it away to open and close it remotely. That's a relay. Electromagnet. DO5, what type of circuit controls the amount of voltage from a power supply? Okay, the circuit is a regulator circuit. A regulator regulates the amount of voltage from a power supply. If you need a 13.8 or 5 volts to charge your cell phone, for example, or whatever, it uses a regulator. You're going to get that one right. Don't overthink that one. All right, DO6. A component is commonly used to change 120 volt AC house current to a lower AC voltage for other uses. Talked about earlier, the transformer. It's a coil of wire and a second coil of wire. They're close together, and the 120 volts comes into this one, and some of that voltage transfers to the other one. In this case, 12 volts. Okay, and 120 volts on this side, 12 volts on this side. And that's done by inductive coupling. You don't need to know that for the technician, but that's how that works. Okay, and a transformer achieves that result. I know a lot of these components might be foreign to you, but let's just keep going here. DO9. Let me find DO9 here. DO9, okay. T6 DO9, top of 168. What's the name of a device that combines several semiconductors and other components into one package? Well, that's called an integrated circuit. They're everywhere nowadays. Pretty much everything, all the devices today have integrated circuits in them. Integrated circuit. Okay, what is the approximate amount of change? Okay, now we're going to talk about dB. Decibels, dB. It measures the amount of change between two signals. 3 dB is a doubling of the signal, or if I said 3 dB less, this one is 3 dB less than this one, it's half. So it's a double or it's half if I say 3 dB, depending whether I say up or down. Okay, just remember that. 3 dB, doubling. As a rule of thumb, 10 dB is 10 times bigger or 10 times smaller. Okay, 10 dB is 10x. 3 dB is a double. You cannot extrapolate in between, but those two you need to remember. All right, so some of these questions are going to be asking you how many dB something is as compared to something else. All right, decibels. Okay, so here we go. T5B09. This is fun. What is the approximate amount of change measured in decibels of a power increase from 5 watts to 10 watts? 5 watts to 10 watts. How many dB? 3, right. 3 dB. 5 watts to 10 watts is a 3 dB increase. All right, simple. I want you to remember 3 dB. Okay. Let's see what's next here. T5B10. What is the approximate amount of change measured in decibels of a power decrease, now a decrease, from 12 watts to 3 watts? 12 to 3 watts. Okay. It's minus 6 dB. And how we get there, the 12, if we go 3 dB, it becomes 6 because it's half. And then 6 to 3 is half also. So you add up the minus 3 dB that got you halfway there, and then the minus 3 dB that got you the rest of the way there, and that equals minus 6 dB. So from 12 watts to 3 watts, the difference is minus 6 dB. Okay? They're no more complex than that. That's exactly how it works. T5B11. What is the approximate amount of change measured in dB of a power increase from 20 watts to 200 watts? 20 to 200. Remember the rule of thumb. 10 dB is 10x. So 20 watts, 200 watts. It's exactly 10x. And 10 dB is the correct answer. Okay, rule of thumb. 10 times increase or decrease is 10 dB. Okay. B07, the abbreviation LED stands for light emitting diode. I think everyone will probably get that one right. LED is a light emitting diode. Come in all kinds of different colors now: blue, yellow, green, red, so on. All right. D07, which of the following is commonly used as a visual indicator? Guess what? It's an LED. It's a visual indicator. It lasts forever practically, and it's very low power consumption. They make great indicators for radios, and they're in your car now. Even your headlamps can be LED. Okay. T5B02. What is another way to specify a radio signal frequency of 1,500,000 hertz? Okay, 1,500,000 hertz can be represented in a number of different ways. It can be represented as, in this case, as 1,500 kilohertz. Okay, 1,500 kilohertz, or 1.5 megahertz. 1.5 megahertz is the same as 1,500,000 hertz. If you know anything about computers, you can look at your processor speeds as 1 gigahertz processor, for example. What is that? That's 1,000 megahertz. 1,000 megahertz is 1 gigahertz. Just like 1,500,000 hertz is the same as 1.5 megahertz, or 1,500 kilohertz, just by moving the decimal point 3 places. A few questions that have to do with converting back and forth. B13, if a frequency readout shows a reading of 2,425 megahertz, what frequency is that in gigahertz? Okay, it's not like the flux capacitor. 2425 megahertz is going to be the same as 2.425 gigahertz. Think of your processor speeds. It's exactly the same way that works. Okay, 2.425 gigahertz is the same as 2,425 megahertz. Okay, BO3, how many volts are equal to 1 kilovolt? Kilo means 1,000, so a kilovolt would mean 1,000 volts, right? And the answer is 1,000 volts. A kilovolt is the same as 1,000 volts. All right. BO6, we're at the bottom of page 170. If an ammeter calibrated in amperes is used to measure a 3,000 milliampere current, what reading would it show? Okay, milliampere goes to smaller. Mega goes bigger. Milli goes smaller. Okay. The answer is 3 amperes. 3 amperes is the same as 3,000 milliamperes. Okay, just like megahertz is the same as 1,000 megahertz is the same as a gigahertz. 3,000 milliamperes is the same as 3 amperes. Okay, so it goes three places to the left. There is a conversion chart in the bottom of 170, and there's a number of prefixes here. We're familiar with mega and giga, and maybe even tera, but there's peta and exa, and on this side, on the small side, we've got milli, and we've got micro, nano, and pico, and they keep getting smaller. Femto and atto. Atto, yeah, that's small. I don't use that one too much. All right. B12, which of the following frequencies is equal to 28,400 kilohertz? Okay, I'm looking at the answers. The answer, there's a megahertz that matches 28,400 megahertz is the same as 28,400 kilohertz. Okay, move the decimal point. All right. Which of the following is equivalent to 500 milliwatts? Milliwatt, 1,000 milliwatts is like 1 watt. So 500 milliwatts is like a half of a watt, and that is the answer, half a watt. Move the decimal point. Okay. How many milliamperes is 1.5 amperes? 1.5 amperes. How many milliamperes? Okay, it's going to be 1,500 milliamperes. Move the decimal point 3 places to the right. Okay, and that's the answer. As easy as that. How many microfarads are 1 million picofarads? Okay, now microfarad and a picofarad are 6 decimal points. 6 decimal points between the two of them. So how many microfarads are 1 million picofarads? Answer is 1 microfarad. Okay, so if you get familiar a little bit with this right here, you're going to understand these conversions. And you're not going to get a lot of these questions. You're probably going to get 1, or we might get 2. So, all right. T5B08. Which of the following types of solder is best for radio and electronic use? Okay, solder. Rosin core solder is the best. Rosin core solder. And maybe I'm not going to go into the other ones, but rosin core solder is the correct answer. So we want to get the correct answer? Yes. Okay. T5B04. How many volts are equal to 1 microvolt? 1 microvolt is equal to 1 millionth of a volt. Micro means 1 millionth. So 1 microvolt is equal to 1 millionth of a volt. Micro. All right. Okay, I think we got this one already. DO8. Which of the following types of solder best for radio and electronic? And rosin core, right? Rosin core. What is the characteristic appearance of a cold solder joint? A poorly soldered joint is called a cold solder joint. And it's grainy and it's dull. Grainy and dull. A proper solder connection is nice and shiny. D07, which of the following measurements are commonly made using a multimeter? Okay, a multimeter, voltage and resistance. My meter here is a multimeter. This is a multimeter. It does multiple things. It's got a little battery load tester on it on this side. It does voltage. It does AC voltage. It does resistance in ohms. It has some amperes reading. It can read amperes. It can check some components as well. Multimeter. They're not real expensive, but you can spend more. That's for sure. I've got a little cheap one. It looks pretty good. We're going to talk about a little bit more about that in the safety section also. Okay. D11. Which of the following precautions should be taken when measuring circuit resistance with an ohm meter? Okay. Ensure the circuit is not powered up. Ensure the circuit is not powered up when checking with an ohm meter. You're likely to damage your brand new multimeter by measuring voltage if you accidentally leave it in the ohms reading setting. Okay, so don't do that. Which of the following might damage a multimeter? Of course, don't measure voltage with the ohms setting. Ohms are for resistance. Okay, D710, top of 174. All right, let's see here. Okay, what is probably happening when an ohm meter connected across an unpowered circuit initially indicates a low resistance and then shows increasing resistance with time? Okay, so you first connect it, it shows low resistance, and then the meter starts going up to high resistance. What do you think is happening there? What's happening is the circuit contains a large capacitor, and it is storing the energy provided by your leads that's trying to measure the resistance. And as it charges up, it can only hold so much power, so your leads start to show more resistance at first, low resistance, and then later high resistance when the capacitor cannot accept any more electrons. Okay, so the answer is the circuit contains a large capacitor, and that's how you can tell. All right. Okay, we are at the end of that section. I think we're going to call an end to this this section, and we're going to have a part 5 coming up. And so we are on page 170. We got through to 174 in our Gordon West Technician Class License Manual. I really appreciate watching. I'm hoping some students, some of my students, and other students get a benefit from this this video, and we can maybe think about doing the general. We'll see. We might do the general next, and maybe the extra. We'll see. So we're on 174. We're going to start with antennas next on part 5. Thank you very much for watching Sunday night, November 13th, here in Southern California. This is Jim, AG6IF. I do have a QRZ page full of information if you're interested. I also have a number of YouTube videos numbered in the hundreds of things I find interesting, and so please feel free to look through there and subscribe if you would like. So anyway, thank you very much for watching. Have a great day tomorrow. This is Jim, AG6IF saying 7-3.